Hello and welcome to this training module about near-field communications and radio frequency identification technology. Now, when you're done here, you'll have a sound basic understanding of how NFC and RFID work and some of the advantages and disadvantages of various RFID techniques. And by the way, you've come to the right place to learn about NFC and RFID. Maxim is a leader in the development of these technologies. We can help you with the chips and the technical expertise to make these designs really easy. Okay, ready? Let's get started. We'll start by defining NFC and RFID, and then we'll move on to look at some typical applications of how certain RFID technologies are better suited for some applications than others. And finally, we'll look at the technical characteristics of these technologies. Now, NFC and RFID fit within the broad definition of wireless communication technologies. Now, like any wireless technology, the whole idea is to move information from one point to another without any physical contact or wired connection. Wireless technologies rely on electromagnetic waves that travel from the transmitter to the receiver. Information is modulated onto a carrier at the transmitter and demodulated from the carrier to be used at the receiver. Well, that's the way to think of NFC and RFID. They're really just specialized RF links, and in a sense they're no different from the more familiar radio frequency technologies like cell radios, Wi-Fi networks, and Bluetooth. Of course, there are differences in the specifics: frequency, modulation schemes, bandwidth, data rates, media access rules, radiated power, effective range. But in the end, all of these technologies that use radio frequencies to carry information operate in the same fundamental way. A transmitter modulates information onto a carrier. A transmission medium propagates the modulated carrier to the receiver, and the receiver demodulates the received carrier to recover the information. A typical RFID system contains all the basic RF front-end components. There's an antenna, a receiver, a transmitter, a modulator, a demodulator, and all the other elements you might expect to find in a radio system. Now, you probably already noticed that some of these blocks have unfamiliar names. For example, the transmitter in the system might be called a tag or a transponder. And instead of a receiver, we might talk about a reader. And don't be confused, all these familiar elements are there, just maybe they're renamed a bit. In some RFID systems, you'll have a transmitter and a receiver on one or both sides. We'll show you how these systems work as they come up. Okay, this is a good time to talk about what we actually mean by RFID and NFC, and the differences between them. RFID stands for Radio Frequency Identification. RFID refers to any system that uses radio waves to read and capture information stored on a tag that can be attached to an object or a person. An RFID tag can be read from up to several feet away and does not need to be within direct line of sight of the reader to be read. NFC stands for Near-Field Communications. Now, NFC is best thought of as a subcategory within the RFID universe. While the broad definition of RFID spans many RF technologies, NFC is defined by very specific standards for operating frequency, types of modulation, emitted power, range, and bitrate. Now, in short, NFC is more focused on secured systems that govern operations like payment and access control, where confidentiality and data protection are essential. The bottom line is this: you can think of NFC as a specialized instance of RFID. Now, not all tags are created equal. There are active tags and there are passive tags. There are even semi-passive tags. You need to know how these tags work to really understand RFID and NFC. Now, a passive tag has no energy source. To operate, it has to harvest energy from the RF carrier that's transmitted by the reader. Now, of course, that means the range is going to be severely restricted. But passive tags are less expensive, and they're more robust since they don't require a battery to operate. Active tags, on the other hand, do contain a battery. That introduces a few issues that a designer has to consider. Space for the battery, environmental accommodations for the battery, operating life, cost, for example. But the advantages are many. The tags can have larger memories and you can read them from a greater distance. In addition, an active tag can announce its presence by transmitting a periodic beacon. A passive tag can't do that. Now, semi-passive tags harvest energy from the reader to power the radio, but they contain a battery to maintain the logic within the tag. This table gives you a broad idea of the operating characteristics of some RFID and NFC systems. One thing you'll note is that NFC uses the 13.56 MHz high-frequency band and amplitude shift keying for its communications. RFID systems can use a variety of bands from sub-100 kHz all the way up to microwave bands and lots of different modulation techniques. But there's one thing you just can't get around. NFC only works at short distances, less than about 10 centimeters. Many RFID techniques will work at around a meter for passive tags and as much as a kilometer for active tags. That difference illustrates some significant differences in use cases between NFC and more generic RFID. With its short range, NFC can be more secure than generic RFID, simply because it's more difficult for an attacker to eavesdrop on the communications. And that security makes NFC much more suitable for payments and access control than generic RFID. This chart gives you an idea about where RFID and NFC are positioned with respect to their other RF communication cousins. Now, the main takeaway here is that RFID occupies the same short-range networking space as Zigbee, Bluetooth, and to some degree Wi-Fi, but at a much lower data rate. And while NFC can support slightly faster data rates, the short range makes it really unsuitable for general networking purposes. Better to leave the heavy lifting to Wi-Fi and the various cellular standards. But the short range and modest data rates are ideal for the low power, small data packet world of payments and access control. This table shows some examples of RFID applications and their frequency ranges. The low frequency range covers frequencies less than 135 kHz. Now, at this frequency, the transmitter and receiver are always in the near field, and you'll usually see systems operating at this frequency in applications like waste sorting, medical ID, and alarm systems. The high frequency range centers around 13.56 MHz. Now, this is the world of NFC. And here you'll find a wide range of applications that include contactless payment cards, mobile wallets, ticketing and fare coordination systems for public transport, automated baggage management in airports, and systems to assist caregivers in wellness and healthcare applications. The UHF range includes the 433 MHz band for ITU Region 1, that's mostly Europe, and the 900 MHz band for ITU Region 2, that's mostly the Americas. These bands are frequently used to locate shipping containers and in manufacturing to track material. Finally, the microwave region falls in the 2.45 GHz and 5.8 GHz ISM bands. And these bands, the wavelength is on the order of a few centimeters, so you're generally operating in the far field. You'll see tags operating in this frequency range frequently used in automatic highway toll systems. The range of applications for RFID is nearly infinite. Every domain that involves items that need to be identified, located, or tracked within a limited range from a few centimeters to a few hundred meters are good candidates for an RFID-based solution. Think about it. Vehicle tracking, factory automation, access control, animal identification and tracking, and so many other applications. All of these are areas that can benefit from RFID systems. Think about factory automation. Put an RFID tag on raw materials, work in progress, and finished goods, and now you can easily identify, locate, and track the goods as they move within the factory and between buildings. And in addition, every step of manufacturing, fabrication, packaging, weighing, test can be recorded at each step. And there's one more benefit. With RFID at each stage, management now has a complete view in real time of every item in the factory with its actual status. Hey, armed with that information, management can make the proper business decision to optimize the flow of goods from raw material delivery to placement into finished goods. Now, there's one application that hasn't seen a lot of adoption yet, and that's implanting passive RFID tags under the skin. Nevertheless, there appears to be a trend in U.S. hospitals to apply this technology, and particularly with patients with debilitating conditions like Alzheimer's disease or advanced diabetes. In these applications, medical professionals can ensure that the right medication is administered in the proper dose, even if the patient can't reply. Non-medical applications for implantable RFID tags include access control. An RFID tag can be used as a smart key that can't be stolen or duplicated for situations where access to sensitive information or materials dictates the highest level of security. NFC applications have to work within the range constraints of NFC, typically a few centimeters. But it's a mistake to think of this as a limitation. The short range makes NFC especially well suited for communication between paired devices that only need to communicate when they're in close proximity and where security concerns would preclude longer range solutions. The best example of this is payment systems. There's just no reason to broadcast your credit card information to anyone who might be listening. But payment is not the only application. Consider exchanging contact information, access control to a building, an office, or a safe, ticket management for public transport, even something as seemingly frivolous as interactive toys. All of these devices can use NFC to exchange information and improve the user experience. Contactless payment alone is becoming huge. Both merchants and customers are adopting it because it's more convenient and more secure. Just tap the credit card, your phone, or your watch, and you're ready to go. One can envision a future in which it will be difficult to shop, dine, or ride on public transport without an NFC system in a credit card or a mobile device. Now, let's talk about security. NFC is ideal as a smart electronic key. Codes can be exchanged with a lock to guarantee access only to authorized parties. Think about hotels, workplaces, really any place access control is needed. Now, don't run past the security aspects of NFC. Because this is a two-way exchange of data, it's not difficult to implement a cryptographically strong challenge response system. And remember, Maxim has a long history that goes back 3 decades providing data protection solutions and secure devices. The most common tag form is the flat, square, multiple copper coil antenna with a tag in the middle. You've seen them everywhere. They're just ubiquitous. But there's also a paper tag. On one side is the printed antenna and the tag chip, and on the other side is a traditional barcode. Products bearing this kind of tag can be read by either a barcode reader or an RFID reader. Another popular form is the encapsulated coil and tag in a hermetic glass container just a few millimeters long. Now, this kind of tag is frequently used for animal identification. And just as there are many different kinds of RFID tags, RFID readers, and eventually RFID writers as well, can take different forms, from an anti-theft system that stands guard at the exit doors of department stores, to portable payment terminals for on-the-spot point of sale, and all the way up to peer-to-peer communication devices embedded in mobile phones that act as both reader and transponder. Now, in this latter case, 2 people can exchange data like business cards, pictures, financial information, all just by bringing their devices close to one another. Okay, now it's time to get down to the technical details of how RFID actually works. Most RFID systems, including NFC, use the ISM bands. Now, ISM stands for Industrial, Scientific, and Medical, and these frequency bands have been designated as license-free by most regulatory agencies, so long as the emissions and the equipment meet certain technical requirements. Frequencies below 100 MHz with wavelengths longer than about 3 meters are called inductive frequencies, and frequencies above about 100 MHz with wavelengths shorter than about 3 meters are called radiative frequencies. Now here's why. At low frequencies, there is a strong interaction between the transmitting antenna and the receiving antenna due to their proximity relative to the wavelength of the carrier. Effectively, the transmitter and receiver behave as though they were coupled by means of an air-core transformer. Now, this coupling, when in close proximity, is called the near-field effect. But when there is a great distance between the transmitting and receiving antennas relative to the wavelength, the receiving antenna is not directly coupled to the transmitting antenna. Instead, the transmitting antenna is expected to couple the transmitted energy to free space, and the receiving antenna is expected to interface the RF front end of the receiver to free space. Under these circumstances, the receiving antenna is said to be in the far field of the transmitter. Now, most RFID systems operate in the near field. The coupling between the sending and receiving systems is generally inductive, like the coupling observed in an air-core transformer. This coupling dictates most of the behavior observed in RFID systems. The frequencies most often used by RFID systems fall into several broadly defined bands. The low-frequency bands, centered around 125 and 134 kHz, the high-frequency 13.56 MHz band, UHF bands in the 860 to 960 MHz frequency range, and the 2.4 GHz microwave band. Now, in contrast, NFC systems use only the 13.56 MHz high-frequency band. Maxwell's equations govern the behavior of electromagnetic fields and waves, and they describe a distance at which the near-field effects become less significant and the far-field effects start to dominate. This distance is given by the wavelength divided by 2π. At the NFC operating frequency of 13.56 MHz, the wavelength is about 22 meters. That places the near-far field boundary at about 3.5 meters. The near-field region can be further differentiated into two subregions: the reactive region, where the receiving antenna has a significant impact on the performance of the transmitting antenna, and the Fresnel region, where the inductive effects of the receiving antenna have less effect on the transmitter. The specifics about exactly how antenna placement affects system performance is pretty far outside the scope of this discussion, but hey, there are lots of online resources on this topic if you'd like to go further. Now, the coupling that occurs between the reader and the tag in the reactive near field is very much like the coupling that occurs between the primary and secondary windings of a transformer. The only difference is that in NFC, there is no iron core connecting the magnetic lines of force. But like a transformer, a change in the load impedance on the secondary side, that is, in the tag, will be observed as a change in the primary side current, that is, in the reader. Now, this fact is what allows two-way communication between the reader and a passive tag. Once the tag has been powered up, it can receive data from the reader by demodulating the carrier signal, and it can send data back to the reader by just varying the load impedance that the reader sees. Now, this diagram illustrates a simple RFID reader. Now, if you've ever taken a peek inside a radio transceiver, the components are going to look really familiar. There's an RF oscillator and a power amplifier in the transmitter, and a low noise amplifier, a filter, a mixer, and a demodulator in the receiver signal chain. Now, obviously, all the real smarts have to be in the reader. It's the master in the relationship, and it has to manage wake-up, initialization, synchronization with a data stream, demodulation of the received data stream, and managing the baseband. Now notice in this RFID reader, there is no forward data stream toward the tag. The reader just generates the RF field that the RFID tag is going to use for power. Okay, now in the tag, there's frequently a memory device, an EEPROM if the data needs to be changed from time to time, or a ROM if the data is fixed. The memory is generally pretty small, a few kilobytes at most, and it might contain an identifier, a bit of program code, temperature records, fabrication records, location information. Hey, really, it could be anything. But not all readers are quite as simple as the one that we just saw. It's also possible for the reader to send information to the tag to be stored or to govern its operating characteristics. Now, this diagram illustrates one modulation technique called pulse interval encoding. The digital logic that drives the modulator generates a high level to turn on the modulator and a low level to gate the modulator off. In pulse interval encoding, a 0 bit is represented by a short on time followed by a short off time, and a 1 bit is represented by a longer on time followed by a short off time. Now, the modulator in this case is a simple amplitude shift keying modulator. It could be implemented by a voltage-controlled amplifier, or it might even be just a simple gate. Now, of course, one could use other bit representation schemes like non-return to zero, Manchester encoding, or any other mechanism that encodes a higher density of bits per level transition. And similarly, it's possible to use other modulation techniques than ASK, although ASK is the most frequently encountered technique. Now, getting data back from the tag is a somewhat more involved process. First, the reader has to generate an RF field that the tag can rectify, filter, and use for power. But once the tag is powered up and ready to respond, it begins varying the load connected to the antenna. And the second illustration here, the tag is presenting a low impedance to ground to the receiving antenna, causing significant current flow. Because the transmitter is in the reactive near field, there is a similar current flow occurring in the transmitter circuit. This current flow can be sensed by the reader. When the tag presents a high impedance to the receiving antenna, the current path is removed. That's shown in the third illustration. In the transmitter circuit, due to mutual inductive coupling, there's a similar reduction in current. Now, in this way, the tag can vary the impedance in the receiver's antenna circuit, causing a change in the current flow in the antenna circuit of the transmitter, and that's how the tag gets data back to the reader. All right, now we're ready to take apart a typical tag and see what's in there. Everything starts with the antenna, and that's often in the form of a printed coil. In the case of a passive tag, there's a circuit that rectifies and filters the received signal to harvest enough energy to run the electronics in the tag. Now, in parallel, another diode capacitor circuit acts as an AM demodulator that extracts the data from the carrier. The data can be instructions, measurements, new status information that needs to be stored in the integrated memory. It could be anything. The tag can also be interrogated for stored information. When the tag logic receives a command that requires a response, it begins sending the encoded bit stream to the FET to modulate the load on the antenna. The antenna, actually the secondary coil of a transformer that's made up of the reader coil and the tag coil, is opened or shorted according to the encoded bit stream coming from the tag logic. This bit stream induces current variations in the primary side of the transformer that's in the reader. Now, in this figure, you see a practical implementation of the back-channel load modulation. The top trace is a Manchester encoded data stream coming from the tag logic. A high to low transition represents a 1 bit, and a low to high transition represents a 0 bit. The second trace represents subcarrier modulation. In this case, the 13.56 MHz carrier will be on-off modulated at 1/16th of the carrier frequency to give a subcarrier frequency of 847.5 kHz. The third trace represents the waveform that goes to the antenna switch. When the level is a 1, the switch is open, so is the antenna loop. When the level is a 0, the switch is closed, and the antenna loop is shorted. Finally, the bottom trace shows the RF energy that you can expect to see in the reader antenna. The reader interprets a varying carrier as a high level in the recovered Manchester data stream and a constant carrier as a low level in the recovered data stream. By decoding the data, the reader recovers the 106 kilobit per second data stream. And that's it! Now you know the basics of how near-field communication and RFID work, and some of the applications for the technology.
For more information on this topic, please go to our website at www.maximintegrated.com under Products, Embedded Security, NFC/RFID. Thank you for watching this video, and see you again in another educational video of Maxim Integrated.